Right now, physicists are in the middle of a high-stakes race. But they're not building a faster car or a taller skyscraper. No, they're trying to build the entire universe inside a computer. So let's dive into this absolutely extraordinary quest to simulate reality itself. On the surface, it seems like a pretty reasonable question, right? I mean, we have these massive supercomputers that can model entire galaxies and predict the weather. But the second we try to simulate the fundamental, jittery quantum fields that actually make up everything, even our most powerful machines just completely seize up. Why is that? Well, the brilliant physicist Richard Feynman basically hit the nail on the head all the way back in 1981. He understood that our everyday classical rules just don't apply at the quantum level. To build a model of a quantum system, you need a quantum tool. You can't build a Swiss watch with a sledgehammer, and you definitely can't simulate nature with a normal computer. Okay, first up, let's really get into the weeds of this universe simulation problem. What is it about quantum reality that just completely shatters our standard approach to computing? Well, the answer lies in a property that is famously, well, spooky. It really all comes down to this one thing: entanglement. When quantum particles interact, they can get linked in this bizarre way where you can't describe one without describing the other. Their individual uncertainties kind of merge into this one shared collective state. You measure one, and you instantly know something about the other, even if it's clear across the galaxy. Now here's where the real headache begins, the complexity. Tracking two entangled particles is, manageable. 3 gets a little tricky, 4 harder still. But it's how it gets harder that really matters. See, it doesn't just get a little harder. As one physicist, Mikhail Lukin, puts it, at a certain point, the math just exponentially explodes. The amount of information you have to track grows so ridiculously fast that you run out of memory on any classical computer you can possibly imagine. This is the computational wall. So, how in the world do you get past that wall? Well, that brings us to the first team in this race, the digital, or bit-by-bit approach. I want you to think of them as the architects, trying to build a totally programmable quantum world that can simulate the universe, one logical step at a time. And hey, this isn't just a theory on a whiteboard. This is real hardware. Processors, just like this one from Google, are already simulating these tiny little patches of quantum fields. They work with the basic building blocks of quantum information. But some teams are kicking it up a notch. Okay, so we're all familiar with bits in our regular computers, and most of us have heard of qubits in quantum computing, which can be a 0, a 1, or both at once. But now, meet the quidit. Instead of just 2 states, a quidit can hold 3, 4, 5, or even more states all at the same time. It's a massive, massive information upgrade. And the power of that upgrade is just staggering. For one team at the University of Innsbruck, switching from qubits to quidits shrank the algorithms they needed for their simulation by a factor of 10. A 10x improvement, just like that. I absolutely love this quote from Christine Muschik, one of the lead researchers on this. She said using qubits was like putting the algorithms on a diet. They just became leaner, faster, and way less prone to making errors. It's a total game changer for this digital simulation approach. But the digital architects definitely have some serious competition. And that brings us to our next contender, the analog approach. So if the digital folks are architects writing a complex blueprint, I want you to think of the analog folks more like sculptors, creating a direct physical copy of reality. The core idea here is to build a quantum system that you can control, that behaves in the exact same way, that follows the exact same mathematical rules as the super complex, hard-to-study system you're actually interested in. You're basically building a stand-in. And honestly, the perfect analogy for this comes right from the source material. It's just like putting a model airplane in a wind tunnel. You don't program a supercomputer to simulate all the airflow. You just build a physical model, put it in a controllable environment, and you just watch how it behaves. And from that, you learn about the real airplane. And this is the really crucial difference. This isn't about running an algorithm. You create the setup, like a team back in 2020 that used an array of 71 ultra-cold rubidium atoms to mimic quantum electrodynamics, and then you just let nature take its course. You let the system evolve all on its own, and then you measure the results. So now let's look at the race itself. We have these two incredibly powerful approaches, digital and analog, and they're both accelerating at this unbelievable pace. But what are they actually racing toward? What is the ultimate finish line here? I mean, just look at how quickly things are moving. It's wild. Just a few years ago, we were talking about one-dimensional simulations, and now we're already seeing major breakthroughs in two-dimensional force fields and even simulating how quarks behave. Both teams are just hitting these major milestones, one right after the other. The real trophy, the grand prize for all of this, is to successfully simulate quantum chromodynamics, or QCD for short. This is the theory of the strong nuclear force, the unbelievably powerful force that literally glues quarks together to form the protons and neutrons inside every single atom. If we can crack QCD, we could unlock the secrets of how matter behaved in the very first moments after the Big Bang. And this is where the competition really heats up. Team Digital, with their super powerful quadrants, they argue they're best for precisely modeling these really complex, detailed events, like particles colliding. But Team Analog fires back, saying their approach is way easier to scale up to the huge numbers of particles you need to see the big picture of how quarks and gluons interact. So finally, let's talk about what this all means for the future. We've been framing this whole thing as a race, but as we get closer to that finish line, it's worth asking, is that really the right way to think about it? So, after everything we've seen, who takes the prize? Is it the digital architects with their super precise algorithms, or the analog sculptors with their massively scalable models? Well, it turns out that might be the wrong question entirely. You see, researchers are already developing hybrid analog-digital simulations, trying to get the absolute best of both worlds, the incredible versatility of digital computing with the sheer efficiency of analog evolution. The future might not be a competition at all, but a collaboration. And it's so important to keep some perspective here. As Harvard physicist Mikhail Lukin reminds us, this is quite an interesting time, but it's also quite early. Think about it like this. The Wright brothers have just barely gotten off the ground, and we're already dreaming about going to Mars. Which leaves us with this one final kind of mind-blowing thought. If these are the incredible things we're discovering right now, in the absolute infancy of this technology, what fundamental secrets of our universe will we finally be able to unlock when it's not so early anymore?